Hi everybody, welcome to our video on extreme values. This is our second video in our applications of derivatives section. So to talk a little bit about extreme values of a function. The extreme values of a function are the maximum and the minimum values of that function. We can find the extreme values of a function by first finding the derivative of the function. And we can describe extreme values further as either absolute or local extreme values. Extreme values occur at what we call critical points of a function, and they can also exist at the endpoints of a function. So a critical point of a function, f of x, it's a point where the derivative, dy dx, is equal to 0, or where it doesn't exist. And an endpoint of a function is a value corresponding to a boundary point on a closed interval. For example, for a function f of x is equal to x squared, defined on a closed interval from x is minus 2 to x is plus 2, the endpoints are at f of minus 2 and at f of 2. So to think about what an endpoint is in an easier way, if we look at our diagram at the bottom of this screen, here we've got, looking at the diagram, we've got a function that's being plotted in blue. Well, if we wanted to pay attention to what our endpoints are here, so we've got one endpoint up at the top left of the chart where the blue line begins, and the other endpoint of that function corresponds to the top right of the chart where the blue line ends. So that's a bit of a simpler way of thinking about what an endpoint is. And if we were to find, well, a critical point in this chart, well, that would correspond to the point where x is equal to c at the trough or the bottom of the valley of that graphed function. So the derivative dy dx, that's actually equal to 0 at that point, and we call that point a critical point, and that makes more sense when we think about the definition of derivative and how it relates to slope and rate of change. So our derivative is the rate of change specifically at a point in the function, or it's the slope at a point in the function. And if we remember back to our discussion of slope describes the rise of the function per run. So at any given point, if a function is climbing, if it's going upwards, it'll have a positive slope, which is a positive derivative. And at any given point, if a function is dropping, it's declining, then it'll have a negative slope, a negative derivative. So if we look at the values of the function on the left-hand side of the chart, well, for all of those points, it has a negative slope. The value of the function is decreasing as it goes along. And if we look at the values of the function on the right-hand side of the chart, it has a positive slope all along those points because the function is climbing as x increases along those points. So that corresponds to the function having a negative derivative in the area of the chart on the left-hand side, and it has a positive derivative on the area of the chart towards the right-hand side. But right at the bottom of that trough in the function, the bottom of that valley, right at the center, well, there's a point where the function is not climbing and it's not dropping as x increases either. It's just flat. And that corresponds to a minimum value at a point where the slope is equal to 0 and where the derivative is equal to 0. So by looking for where our derivative is equal to 0, we can essentially find the maximum and the minimum values of our function, which is really useful to us. And it's similar with a maximum. So if you imagine the very, very top of a peak, well, on the one side where you're scaling the peak, your function is continuously climbing and climbing and climbing, which is a positive slope and a positive derivative. And on the far side of the peak, your function is dropping, which corresponds to a negative slope and a negative derivative. But right at the top of the peak, right at that top point, your function is not increasing as x increases, and it's not decreasing as x increases yet either. Your slope is equal to 0, which corresponds to a derivative of 0. So at that point, the derivative of the function is 0 at that maximum value. So that's how we find our extreme values. We look for where the derivative of our function is equal to 0. So what we're going to do now is we're going to take what we've just learned about extreme values and how they relate to the derivative and how we can find those extreme values, and we're going to use that knowledge in solving a problem. So first of all, I direct your attention to the diagram at the bottom of the screen. We've got a river highlighted in blue, and on one side of the river we've got a power station, that grey building, and on the other bank of the river and downstream we've got a town. And if I direct your attention to the text, we can see that there's a power station located on a river, and we want to run a new cable from the power station to the town on the other side of the river. It costs €60 per meter to run a cable underwater, and it costs €40 per meter to run a cable under land. The river is 500 meters wide, and the town is a kilometer downstream from the power station. So what we want to find is where is the least expensive route to run the cable. So initially we can just look at the chart and we can read the problem, and we can see that there's probably a few different options or tactics we could do here. When we look at the cost per meter, it looks like it's most expensive to go underwater. So it's €60 per meter to run cable underwater, but it's only €40 per meter to run the cable under the land. So maybe it might be cheapest to go straight across the water in as minimum distance as possible. So to take the most direct route straight across the river to the opposite bank. And then you could go the rest of the way along the land, and you could do it that way. Or there's maybe another route you could take. You might be able to use less total length of cable if you went in a straight line straight from the power station straight to the town. So if you did it this way, you're always going underwater, so it's the most expensive per meter, but your total length of cable will be less, so maybe it'll work out less. So to think about it a bit more, we can start to put down some distances based on the definition of the problem. We know that it's 500 meters straight across from the power station to the other side of the bank of the river. So we've got that 500 meters there, and we know that from that point to the town is a kilometer or 1,000 meters. And we can use the theorem of Pythagoras to work out the length of the hypotenuse of the triangle, which gives us 1,118 meters. So now we know the length going in a straight line from the power station to the town. So based on this distance information and the information of how much it costs per meter underwater or under land, now we can start working out the costs of our initial ideas. So the underwater cable is more expensive, so we calculate the cost when using the least amount of underwater cable. So by trying to go underwater directly 500 meters across to the bank and then going 1,000 meters along land to the town. So if we did that, the total cost would be 500 meters underwater multiplied by €60 per meter, plus the 1,000 meters under land multiplied by €40 per meter under land. That works out to be 30,000 plus 40,000, which works out to be €70,000. So we have a cost of our first attempt. So we can also look at our other idea as well. Alternatively, we could take the most direct route going in a straight line under the river. So if we did that, we're going along the 1,118 meter route straight from the power station to the town. So every meter is going to cost us €60. So we multiply 1,118 by 60, and that gives us €67,080. So it's actually cheaper to go directly from the power station to the town, even though per meter it's more expensive underwater. So we just guessed those two options though, and they are extreme options. So maybe there's a middle ground that might be cheaper again. So rather than an extreme, minimizing the underwater cable length or going straight to the town underwater, we could try a middle ground approach. So with a middle ground approach, we run cable underwater to the halfway point, 500 meters from the town. And here we use the theorem of Pythagoras again. We've got a triangle with two sides of 500 meters of 500 meters, and when we use Pythagoras' theorem, we get the remaining side is 707 meters. So now we've got 707 meters underwater, followed by 500 meters under land to get to the town. So we can work out the cost of that, running to a point underwater 500 meters from the town. It comes out to 707 meters multiplied by 60, plus 500 meters multiplied by €40 per meter, which works out to be 42,420 plus 20,000, which works out to be €62,420. So this attempt was cheaper again. So this was the cheapest of everything we've tried so far. But this was another arbitrary attempt. What we want to do is we want to find the absolute cheapest option. So we could have a look at, say, running to a point on the other side of the river that's a little bit further away from the town or a little bit closer to the town. And right now, based on the information we have, we're not really sure what's going to be more expensive or cheaper. So our best solution so far involves running the cable to a point 500 meters from the town. But as we just said, we chose this arbitrarily, just at random really. And what we want to do is we want to try and find the best, cheapest solution. So to do that, we can use calculus to find the best, cheapest solution. And the first step is to express the total cost as a mathematical function of other variables. And we can then use calculus to find the variables that give the minimum value of that cost function. So it becomes what we can describe as a optimization problem. And if we look at our graph at the bottom of the screen, what we're really dealing with is it's a problem with two variables, first variable x and a second variable y. So we're dealing with some distance of x across the river along with some distance of y along the land. And for some value of x and for some value of y, that's going to correspond to a minimum cost. So what we're looking for is the values of x and the values of y that correspond to the minimum total cost. So we can express the total cost as a function written in terms of x and y. So our total cost C as a function of x and y is equal to 60 multiplied by x plus 40 multiplied by y. So it's 60 euro per meter multiplied by x, the distance across the river, plus 40 euro per meter multiplied by y, the remaining distance to the town in meters. Well, the important thing to remember here is that the problem becomes much easier to solve if we express it as a function of a single variable. So we can use the theorem of Pythagoras to express x in terms of y. Because if we look at our graph here, we've got our distance x and our distance y, and we also know that if we run our cable in the most direct route across the river, that 500 meters, well, going from that point to the town, we know that that's 1,000 meters. So we can find the distance of the base of that triangle as being equal to 1,000 minus y. So now when we look at our triangle in our graph here, one side is 500 meters, the other side is 1,000 minus y, and using the theorem of Pythagoras, we can express the x side of the triangle in terms of 500 and 1,000 minus y. And that's shown here in the next line of maths. So x is equal to the square root of 500 squared, which is 250,000, plus the 100 minus y term squared. So now what we can do is we can take that representation for x and put it back into our total cost function and express the total cost simply in terms of as a function of y. So we look at our equation total cost C as a function of x of y is equal to 60x plus 40y, and we replace x with our square root 250,000 term. So what we get is the maths equation at the bottom underneath. So that's now displayed at the top of this screen. So total cost as a function of y is equal to 60 into bracket square root of 250,000 plus bracket 1,000 minus y, close bracket squared, close bracket, plus 40y. This is a mathematical function expressing the total cost as a function of a single variable. And we now want to find the value of y that gives the minimum value of total cost as a function of y. So we know how to do this. We search for extreme values by evaluating the derivative of that function, total cost as a function of y. So we find the derivative of total cost with respect to y. So we start off with the total cost as a function of y in that top line, and our derivative of total cost with respect to y, so c prime y, is equal to the term underneath when we apply our differentiation rules. An extreme value occurs where the derivative of c of y is equal to 0. So if we set the derivative equal to 0, the expression simplifies out to 60 into bracket 1000 minus y close bracket is equal to 40 into the square root of 250,000 plus bracket 1000 minus y close bracket squared. And we can solve that expression for y. And when we do that, we get that y is equal to 555 meters, or y is equal to 1445 meters. And from the definition of our problem, only y is equal to 555 meters is within the interval of interest. So we've done a number of steps here. We've expressed our problem in terms of a mathematical function of one variable. We found the derivative of that function and we set the derivative equal to 0, and then we solved for the value of y that corresponds to a derivative being equal to 0. So what we found is we found a critical point of our total cost function. We know that a critical point exists where y is equal to 555 meters. So what we can do now is we can take that y value, sub it back into our total cost function, and find what the total cost is at that critical point. And we know that a critical point is going to give us either a maximum or a minimum value of our function total cost. So here we've got that worked out. The cost at the critical point, y is equal to 555 meters, and that our endpoints, which we already which we already investigated, are the cost at the critical point, where y is equal to 555, is equal to 62,340 euros. The cost at the endpoint, where y is equal to 0, corresponds to 67,080 euros. So that was our route going straight from the power station to the town, straight under the river. And our cost where y is equal to 1,000, taking that minimum underwater route that we looked at first, that corresponds to 70,000 euros. So, having investigated it, the least expensive solution costs 62,340 euros, and it involves running a cable across the river to a point 555 meters from the town. So here we've just used calculus to solve a practical problem. By expressing that problem in terms of a mathematical function, we've been able to express the total cost as a function of a single variable. Then we've gone to look for the extreme values of that function by evaluating the derivative and setting the derivative equal to 0. That's let us find the critical point of our function, which corresponds to a maximum or a minimum value. And we've evaluated the cost at that critical point, and we found that a minimum does exist there. So we found the cheapest solution using calculus. So, in summary, we can use the derivative of a function to learn more about the extreme values of that function. Extreme values of a function can occur at endpoints and do occur where the derivative is equal to 0 or does not exist. By expressing problems in terms of mathematical functions, we can then use calculus to solve optimization problems. In the previous example, we expressed the problem in terms of a mathematical function. We then calculated the derivative, and we found the input variable that corresponded to a derivative equal to 0. This input value corresponded to an absolute minimum value of the mathematical function. So that allowed us to solve our optimization problem. So this was our discussion of extreme values. I hope that you found the information and the practical example really useful. Please click on the next video for more applications of derivatives. Thank you for your time.